Hi everyone, and welcome to our last video on the chapter of capacitance and capacitors. So when you're charging a capacitor, you're doing work. The battery is doing work to move charge onto the capacitor. As a result of this, energy is going to get transferred from the power supply, and it's going to be stored as electric potential energy in the capacitor. A really good example of this is camera flashes. So camera flash units use a capacitor to store energy, and the capacitor takes a few seconds to charge when you connect the battery in the camera. But then the energy gets discharged very rapidly when the capacitor is connected to the flash bulb in order to give a short but a very intense flash. So let us consider, let's try and actually plot out something. Let's plot out the potential difference versus charge. Now we know that Q is equal to C times V, right? So if I were to plot this out, it would be a straight line through the origin. Now I just want you to be careful here. In this case, I've put V as the y-axis. So the gradient of this line is going to be 1 upon C, capacitance, not capacitance itself. It would be the reciprocal of capacitance. Just be careful. So let's move on. So we know that from chapter 17, from the definition of potential, we know that the work done is the product of potential and the charge. So if I were to write that out as an equation, W equals electric potential energy, which is equal to V times Q. If you're not familiar with what I'm talking about, please go back to chapter 17, watch those videos. However, the more and more charge that gets transferred to the capacitor, the potential difference is increasing. So suppose when the potential is V naught, when the charge that is being stored is Q naught, right? So let's plot that up here. So V naught here has a corresponding charge of Q naught. So if you add a further small amount of delta Q, so I'm going to go up to here, let's say, right? So right there. So this is going to be, I'm just going to write it out here like this. This is going to be Q naught plus some delta Q. So you're going to see that a small amount of charge has been applied. So the energy that's being transferred is going to be given by the additional amount of energy is going to be given by delta EP naught is going to be V times delta V naught, I beg your pardon, V naught times delta Q. Infinitesimally small amount of charge added more. So you can assume that V naught is still constant. What do you think this is? Isn't this equal to the area of this triangle right here? Right? Aren't we talking about this additional amount of work that's being done to convert to move charge from the battery to the one plate of the capacitor? So we can essentially, if the amount of charge delta Q is really small, the strips become really thin, and their combined area is just equal to the line, equal to the area between the line and the horizontal axis. So as a result of this, we can say that EP is equal to half times QV. Right, so that is the equation you want to go forward with. This is the expression when you use the battery, energy transfer from a battery in charging the capacitor. And this is electric potential energy, and it gets released when the capacitor is discharged. And because of this guy right here, you can also write this in other ways. You can write it as half CV squared. You could also write it as Q squared upon 2C. All of these are equivalent ways of writing it. So take that camera example again. The flash lamp has a 5,000 microfarad capacitor inside it, and it's got a 9-volt battery, right? And the capacitor is then disconnected from the battery, and the energy, what would be the energy that's transferred when you discharge the capacitor through the lamp, so that at the end of it all, final voltage is 6 volts on this capacitor. So what is the energy change? That's really the question that's being asked here. So the energy change is going to be, what was the energy initially at the initial voltage? So I'll call it V1 squared minus half C at V2 squared. So the voltage has changed basically, right? So we can write it like this: half 5,000 microfarads, or 5,000 times 10 to the negative 6 farads. And then V1 is 9 volts squared minus V2 is 6 volts squared, which is equal to 0.113 joules. Please note that V1 squared minus V2 squared is not equal to V1 minus V2 squared. It's a common mistake that people make. Just be careful, make sure you are doing your algebra correctly. So that's how you would calculate the energy that can be stored on a capacitor. So folks, that brings us to the end of our videos on chapter 18, capacitors and capacitance. I will see you in chapter 19. Thank you.